Okay, so we are gonna repeat or review everything we've done so far one more time. This is to do with energy or escape from the Earth's gravitational field. Okay, all right, here we go. So we said that if I'm on the surface of Earth right here, my EG right here is maximum at negative big G. Mass of Earth, mass of the smaller body divided by R of Earth, and this R of course is the radius from the center of Earth. Okay, and this is my total energy, and when I am leaving the potential well, and when I reach up here on the top, my R approaches infinity and my EG goes to 0. So this is what we talked about so far. Okay, and then we said that if an object is in orbit meaning moving circular motion around Earth in orbit, then the velocity for that object is v circular, which equals to the square root of big G mass of Earth divided by R, and this R right here is R altitude plus RE. Okay. And we said if my object is on the surface of Earth and wants to escape from Earth, and then we said this was V escape, then the square root of 2 big G mass of Earth divided by RE. This is the escape velocity from the surface of the Earth. So basically what we're saying is the total energy at the surface of the Earth is converted into kinetic energy. Okay? If I'm in orbit and I want to escape from orbit, then my velocity was v equals to v escape. Again, the same thing. 2 big G mass of Earth divided by R. Here R again is R altitude plus RE. Okay? We said that if my object is under this R approaching infinity, when it is in the gravitational field of Earth, then it is bound to Earth. If my object is bound to Earth, my total energy is half EG when it is bound to Earth. Half EG. If it's in orbit, it's bound to Earth. If it's in orbit, it's bound to Earth. Yes. Yes. Is the moon bound to Earth? Yes. ISS bound to Earth? Yes. Every weather satellite bound to Earth? Yes. Is the sun bound to Earth? No. We are bound to the sun. We are bound to the sun. We don't get affected. The sun does not get affected by us. Okay? Alright. And the reason is the mass of the sun is 99.9% the mass of the solar system. The mass of the sun is 99.9% the mass of the solar system is inside the sun. And the rest of all the planets put together, including the asteroids and the whatever, make 0.01% mass. So yes, are we bound to the sun? Absolutely. Okay? Alright, we also said that this, if I want to escape from my bound state, when I'm bound, and I want to escape from that bound state, I would need another half EG to be able to escape the potential well from orbit. So this is escape from orbit. So again, if you watched Interstellar, if you watch The Martian, then they are in orbit around Earth and they are escaping from the Earth's orbit. And this is how you would be doing. You would use half of the energy. Okay? Which is why it's easier to make a spacecraft in space than to actually fly it off from the surface of the Earth, because the energy is just too much. Are we okay with this? Yes, question. The V circular. Yes? Well, we are talking about the EK. If I'm in orbit, if I'm moving around Earth, then yes, I have EK, but that EK is based on my V circular. Right? Do I have EK going upward? No. I'm not moving upward. I'm moving sideways. Okay? But if I'm moving upward, then I'm not moving sideways. Does that make sense? If I'm flying my spacecraft from the surface of Earth, I'm moving up, I'm not moving sideways. Right? So this EK is different than this EK. Yes. Yeah, this half EG, yes. Anytime you are bound to Earth, if I'm in orbit around Earth, I will have this energy. Bound to Earth. That's all you need to remember. Okay? All right. So let's do a question. So this is sample problem number 2, Nelson Physics 12 again, page 291. Can I erase this? Anybody want to take a picture? Okay. All right. So page 291, question, sample problem number 2. Great. And the question is as follows. It says a 500 kilogram satellite, mass of satellite 500 kilograms, is to be placed into a circular geosynchronous orbit. Geosync meaning connected to Earth, where we're in sync with the Earth's period. So the Earth's period, of course, is 24 hours. So the period of the satellite is also 24 hours. And it needs to be placed into a geosynchronous orbit around Earth. Okay. The first thing that they want us to figure out is what is the radius of orbit. Part B of the question says, what is the gravitational potential energy on the surface? Part C of the question said, how much total energy of the satellite, what is the total energy of the satellite when it's in orbit? So what is E binding in orbit? Orbit. Okay. And then D is how much work must the launch rocket do on the satellite to place it into orbit? So what is the work required to put into orbit? And E is once in orbit, how much additional energy would the satellite require to escape from the potential well? So what's E escape from orbit? You know, perfect test kind of question. Right? All right, so let's start out first by trying to figure out what my R of orbit is. And for figuring out my R of orbit, I'm going to do FC, which equals to big FG. So mv squared over R, or I should say, because we don't have velocity. So 4 pi squared mr over t squared, which equals to g MEM over R squared. Okay, so when we solve for it, we're solving for R. R comes out to the cube root of G mass of Earth T squared divided by 4 pi squared. Okay, and R equals to the cube root of 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. And then this 24 hours, convert this into seconds, and this comes out to 8.64 times 10 to the 4. So this is 8.64 times 10 to the 4 squared, because that's t squared, divided by 4 pi squared, and your R comes out to 4.22 times 10 to the 7 meters. Now this includes our altitude plus RE, which equals to 4.22 times 10 to the 7. So the question is, what is the altitude? So I'm going to do R altitude, which equals to 4.22 times 10 to the 7 minus 6.38 times 10 to the 6, and you end up with the altitude, which is 3.58 times 10 to the 4 kilometers. Yeah. Why don't you do it? Okay. Let's erase this and do some of the other questions. We don't have that much time. Okay. So now we're going to do part B of the question. Now that we know the R, the next question is, what is my EG on the surface? Well, EG on the surface, we know already, is negative G, mass of Earth, mass of object divided by RE. So that's going to be negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 500 divided by 6.38 times 10 to the 6 meters. And you get EG on the surface, which is negative 3.13 times 10 to the 10 joules of energy. This is the total energy of my system at the bottom. Okay, part B of this question. Part C said, what is the work done to put the satellite into orbit? And for that, it's going to be E total, or I should say, yeah, E total equals to half EG. Okay. If it's bound to Earth, it says the total energy of the satellite. Yeah, what is the total energy of the satellite when it's bound to Earth? So that's going to be half times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 500 divided by 4.22 times 10 to the 7. And you end up with so you end up with the E total, or binding energy, is negative 2.36 times 10 to the 9 joules of energy. So this is binding energy. Okay. Now part D of the question said, what is the work done, to put this object into orbit? How much work was done to launch the rocket and place it into orbit? So I'm going to do W equals to E2, EG2 minus EG1. Okay, so of course we know that EG2 was negative 2.36 times 10 to the 9 joules of energy minus negative 3.13 times 10 to the 10 joules of energy, and you get work which equals to 2.89 times 10 to the 10 joules of energy. And the last part of the question was, how much more energy do I need to escape the field? So that E total escape equals to negative 2.36 times 10 to the 9 joules of energy, actually positive. How much more to escape once it's in orbit?